Hi everyone, my name is Zehua Zeng. Here I'm going to present my work with Professor Leilani Battle. Are we there yet? Evaluating existing perceptual models and theories for automated visualization design. So first of all, I want to clarify a term. What is automated visualization design? So let's assume that you have a complex data set like what people are talking about COVID-19 on social media, or the numbers of confirmed cases, death, or recoveries of each area or country. If you want to create visualizations to better understand this data, there are so many different possible visualizations to choose. How do you know which visualization is the most effective one? So automated visualization designs is a new trend in data visualization research area. The system takes data as an input and then automatically create or choose effective visualizations to help user better understand the data that they are working on. There are some work like Voyager, DeepEye, Data2V, Straggle, and VisML have contributed to this research area. The expectation is in the near future, with this technique, anyone could create visualization for analyzing a new dataset with less or even no specialized expertise. However, different methods were used to build or evaluate these automated visualization design systems. But our community still lack a consistent framework to evaluate the recommended visualization designs. Thus, the strengths, weaknesses, limitations of the system compared to each other still remain unclear. We also observe that the construction of these automated visualization design systems rely on the theoretical and experimental evidence of comparing the quality of one visualization design versus another. So how do we know which one of the recommended visualization design is better compared to the other one? So our goal, which is also our contribution, is that we reviewed the community progress on visualization quality comparison and identified the critical gaps in the literature that prevent the construction of a thorough framework for comparing different visualization designs. We also propose potential research path for filling these gaps. So before we collect the related literature, we defined a visualization space for the evaluation framework. So to our best knowledge, we don't see any other work has illuminated or analyzed the space of all possible visualization designs. So to define this visualization space, we vary the space along two major axes, attribute types and visual encoding channels, which are from the effectiveness ranking of different encodings proposed by Kevin and McGill, and later extended by McKinley. We applied 3 attribute types and 12 visual encoding channels to calculate this space. Here, we don't vary the design space by mark type, since we find that mark types are associated with specific combination of attribute types and visual encodings. For example, if position X and position Y are used to represent two quantitative attributes, then the predominant mark type is point, which will come up with a scatter plot. On the other hand, if position X and length are used with ordinal and quantitative data, then the predominant mark type is bar, which will show a bar chart instead. So we separate the calculation by the number of attributes. As we can see, we provide an example of how 1, 2, and 3 encoding visualization designs look like. So based on our calculation, there are more than 14,000 possible visualization designs in the space. We also use the effectiveness and expressiveness principle proposed by McKinley to prune the space. And there are around 7,200 visualization designs left after pruning. So next, we discuss the assumptions and process of our paper review. So without boundary, the visualization space will be two-barred and also in practical as an input to automated visualization design systems. So we apply some theories from existing literature as a guideline to set some boundary to our defined visualization space. We excluded 3D visualization since 3D visualization proves to be less effective than multiple link 2D views. We only focus on static visualization designs since the design space of animation, transaction, and interaction is still under exploited. And moreover, many visualizations are still designed as static. We also exclude small multiples because it will be unfair to compare a single visualization with multiple visualizations. And we also don't know which one of the multiple views is the main factor on influencing users' visual perceptions and text performance. We only focus on visualization designs with 3 or fewer visual encodings, since we find that the majority of existing paper only started visualizations with 3 encoding or less. So in terms of paper collection, we use some keywords like encoding, perception, effectiveness to search the visualization-related conference or journals. We also ask for recommendations from colleagues to collect papers. So in total, we uncovered 145 candidate papers. We then propose 2 main design decisions to exclude unrelated papers. We only keep papers that focus on human perceptions and text performance or emphasize comparison of different visualization designs. So these filtering steps left 76 papers for our analysis. So after the clear definition of the visualization design space and the paper collection process, we now seek to understand how well the related literature covered this space. So we separate the existing literature into 2 categories, theoretical principles and experimental evaluations. So theory papers are critical for helping us reduce the design space. With principles inform us which designs may not be effective, we can potentially reduce the amount of experimental data that must be collected to rank different visualization designs. On the other hand, experiments often lead to the formulation of new theories or the refinement of existing ones. So we find that theoretical papers cover well for one encoding visualization designs, especially on color, hue, and saturation. However, few of the 2 and 3 encoding visualization designs are discussed. So for 2 encoding visualization designs, only 3 chart types are mentioned, which are scatter plots, line charts, and bar charts. For 3 encoding, only 1 combination of visual encoding is covered. So in summary, existing theory does a good job of comparing very simple visualization designs, but does not seem to be actionable for more realistic visualization designs. So compared to theory work, experiment paper cover more visualization designs. However, we find that the experimental literature appears to be imbalanced in assessing different visual encodings. Only a few visual encodings are well studied, like position, length, and color, but the majority of encodings still remain untested. As we mentioned, position, length, and color are the best 3 well-discussed visual encodings. So for position encoding is usually well discussed in paper that focus on multi-class scatter plot or predicting human perception on scatter plots. So on the other hand, length encoding is discussed in paper that more focus on measuring the perceptual bias of length encoding or assessing the effect of visual embellishment on length encoding. So for color, paper are more focusing on evaluating a couple of different color maps or assigning color in a more meaningful way in data visualization designs. So in summary, the overall coverage is low. As we can see from the pie chart, both theory and experiment cover very few multi-encoding visualization designs. So besides the critical gaps in the design space coverage, we also find some inconsistency and conflicts in the literatures. So one of them is the inconsistent encoding classification. Like for a common chalk type pie chart, researchers treat it as angle encoding before, but a more recent work suggests that humans perceive pie charts primarily as area encoding. We also find that different evaluation metrics were used to analyze task performance. Like some paper are using accuracy, but other are using error rate or log absolute error rate to analyze task performance. On the other hand, even experiments are similar, we find contradictory results. Like some research find no perception bias for position encodings, but another research find user tends to overestimate position encodings. So after discovering the gaps, inconsistency, and conflicts in the existing literature, we summarize some research area that the community can focus on to better cover the visualization design space. For example, the experimental literature only covers approximately 20% of all possible visualization designs. This suggests that we lack an overall understanding of how these visualization designs performs in the real world. So we need more comparative experiments to provide enough evidence as an input to automated visualization design systems. On the other hand, existing theory only provides strong coverage for a few possible designs. Most of them are very simple ones. Thus, we need more theoretical principles to save our efforts in designing experiments to evaluate the effectiveness of various visualization designs. Moreover, universal metrics for accessing subjects' performance is also super important for integrating the experimental results in the future. We also observe that machine learning is becoming a more popular approach for automating the visualization design process. However, machine learning models still remain black boxes for humans. They are representing the machines, but not our own understanding of effective visualization design. Thus, we need more holistic evaluation of data-driven models to help us transfer the machine understanding to human understanding. Here, we're gonna discuss some potential future work. So during our annotation process, we find that default mark types works for the majority of the cases. But we also notice that sometimes it can be confusing, like tree map and pie charts fall into the same annotation, the combination of area and color hue encodings. In the future, we could add mark type to our framework to eliminate this confusion. During our analysis, we also observed that the community used different tasks to evaluate human perceptions. It could be interesting to add task type into our framework to see how different task type influence the experimental results of human perceptions and performance. There are also other factors may influence the effectiveness of a visualization design, like a visual aesthetic, intuition and metaphors, background and preference. We could potentially include all these factors in our framework by the time they are well exploited by the community. So let me summarize the three main takeaways from this talk. because the community lacks a consistent framework to evaluate automated visualization designs. Thus, we conduct a literature review to learn the community progress towards a complete framework to compare the quality of different visualization designs. We find that theory paper cover well on one encodings, but few on multi-encoding visualization designs. Although experiment paper cover more visualization designs, only position, length, and color encoding are emphasized, while other encodings still remain untested. So we suggest more comparative experiments, theoretical principles, universal metrics, and holistic evaluation on data-driven model to be contribute to our community toward a complete framework to evaluate automated visualization designs. So that's it. Thank you so much for listening to my talk. If you have any questions, feel free to reach me out by email. Thank you. Bye-bye.